Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In episode 107 of the Network Plus Prepcast, we explore the world of port aggregation, also known as link aggregation, and examine how the Link Aggregation Control Protocol, or LACP, enables switches to bundle multiple physical connections into a single logical channel. Port aggregation is essential in enterprise environments where both bandwidth and reliability are critical. Instead of relying on a single connection between devices, administrators can combine several physical interfaces to increase throughput and ensure continuous operation in case of link failure. Port aggregation works by treating multiple Ethernet cables between two network devices as one logical connection. This bundling process increases the total available bandwidth and provides redundancy. If one of the aggregated links fails, traffic can continue flowing across the remaining active paths without manual intervention. This resilience makes aggregation particularly valuable for connections between distribution and core switches, or between switches and servers that require consistent high-speed access to the network. It also simplifies management by consolidating multiple links into a single interface for monitoring and configuration. At its core, link aggregation is a Layer 2 technology. The switch combines multiple physical interfaces into a single logical interface called a port channel or ether channel. Traffic is then distributed across the participating links based on a load balancing algorithm. Because the links operate as a unified group, administrators can manage them as one entity, greatly simplifying configuration and troubleshooting. This bundling allows network designers to meet bandwidth requirements without upgrading to faster, more expensive links, simply by aggregating multiple standard interfaces. LACP is the standard protocol used to control and manage link aggregation, defined in IEEE 802.3 AD. LACP allows switches to negotiate and automatically form an aggregated bundle. It checks the status, configuration, and compatibility of each participating link before including it in the port channel. If a mismatch is detected, such as different speeds or VLAN settings, the link is excluded from the bundle to maintain integrity. This dynamic verification process makes LACP more reliable and flexible than manually configured static aggregation. It's important to distinguish between LACP and static ether channel. Static ether channel requires the administrator to manually configure and maintain the aggregated links, with no protocol verification between devices. This method can work, but it is error-prone, especially when there are configuration mismatches. LACP, by contrast, dynamically negotiates and maintains the link bundle, automatically detecting changes and adjusting the configuration as needed. This reduces administrative burden and enhances compatibility, especially in large networks or environments where ports may be added or removed regularly. Before aggregation can be successful, certain requirements must be met. All links in the bundle must have the same speed and duplex settings. A mismatch here will prevent the affected link from joining the port channel. Additionally, VLAN configurations and port settings must be identical. LACP cannot aggregate links that are configured differently. Even switch models or firmware versions can sometimes impact compatibility. Ensuring that the physical interfaces match in capability and configuration is essential before bundling can take place. LACP operates in two different modes, active and passive. In active mode, the switch initiates the negotiation process and attempts to form a link aggregation bundle with its peer. In passive mode, the switch waits for a request from the other end before forming the group. For a bundle to be created, at least one end of the link must be in active mode. If both ends are passive, no aggregation will occur. Understanding these modes helps ensure that aggregation takes place successfully, especially when configuring links between different vendors or platforms. Once a port channel is formed, traffic needs to be distributed across the member links in a balanced way. LACP uses load balancing mechanisms based on hashing algorithms to achieve this. These algorithms may use source and destination MAC addresses, source and destination IP addresses, or even TCP or UDP port numbers to determine which link a packet uses. This method helps avoid collisions and maximizes throughput. It's important to understand that load is not perfectly equalized, but rather distributed logically based on the selected hashing method. There are several significant benefits to using LACP in a network. First and foremost is link redundancy. If any one cable fails, the others continue to carry traffic without interruption. Second is improved bandwidth. Multiple links combine their capacity into a larger pipe. Third is simplified management. Rather than configuring each interface individually, administrators configure a single logical interface that includes all participating links. Finally, LACP provides automated failure detection and recovery, further reducing the need for manual intervention during outages or cable swaps. To configure LACP on a switch, administrators first define a port channel interface, also known as a logical interface or bundled group. Then, physical interfaces are assigned to the port channel and set to use LACP mode, either active or passive. Switch commands may vary depending on the vendor, but the core steps remain the same. Identify which ports to aggregate, ensure consistent configuration, and activate LACP. The switch will then handle negotiation, bundling, and monitoring of the link group. Verification is a key part of successful link aggregation. Network professionals use commands like show ether channel or show port channel summary to check the status of port bundles. These commands provide information such as which ports are members, whether they are up or down, the LACP mode in use, and the protocol used to maintain the bundle. They also display any inconsistencies or misalignments, helping identify links that failed to join the group. Monitoring traffic distribution across the bundle can help assess the effectiveness of load balancing and identify bottlenecks. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Troubleshooting port aggregation involves identifying mismatches or misconfigurations that prevent links from forming or operating within a port channel. One of the most common issues is mismatched settings across member interfaces. If even one link has a different speed, duplex, or VLAN assignment than the others, LACP may exclude it from the bundle. Another issue arises from misaligned LACP modes. If both sides are set to passive, the negotiation will never initiate. Additionally, physical layer problems, such as faulty cables or transceivers, can prevent interfaces from joining a bundle or cause intermittent connectivity. Each port channel is assigned a unique identifier or number. This port channel ID must be unique per device and used consistently in configuration. Depending on the switch platform, there may be a limit to how many port channels a device can support, based on hardware or software constraints. Documentation and standardized naming conventions help prevent conflicts, especially in large environments where multiple engineers may be configuring switches. Keeping a clear record of port channel numbers and their associated interfaces avoids confusion and speeds up troubleshooting. One of the key design benefits of LACP is that it helps prevent loops. Because aggregated links are treated as a single logical connection, spanning tree protocols view the bundle as one path, not multiple parallel links. This simplifies loop prevention and ensures stable topology behavior. Without aggregation, connecting multiple cables between switches could trigger spanning tree to block redundant links, negating the bandwidth benefits. By bundling the links into a single port channel, spanning tree sees them as one, allowing full utilization of all aggregated paths without compromising loop-free design. Port aggregation is also fully compatible with VLAN trunking. A port channel can be configured as a trunk, carrying multiple VLANs across a single aggregated link. This is especially useful when connecting switches in a multi-VLAN environment, or linking access layer switches to the distribution layer. All VLAN configurations must be consistent across member interfaces. If one port in the bundle has a different allowed VLAN list or native VLAN, it may be dropped from the group. Proper synchronization ensures that traffic from every VLAN is preserved and forwarded appropriately across the trunk. At the core and distribution layers of the network, port aggregation plays a vital role. High-throughput connections between switches must be fast, resilient, and reliable. LACP enables these properties without requiring extremely high-speed interfaces on each switch. Instead of using one 40 gigabit port, for example, network designers can bundle 4 10 gigabit links. This offers redundancy and allows partial capacity to remain available even during a link failure. LACP thus provides a practical and flexible way to scale bandwidth and fault tolerance in high-demand network segments. LACP is particularly useful in multi-vendor environments. Because it follows the IEEE 802.3AD standard, it enables consistent behavior across switches from different manufacturers. This avoids the compatibility issues often associated with proprietary aggregation protocols. As long as both devices support LACP and have properly configured ports, aggregation can be established seamlessly, even across different switch families or brands. This standardization is vital in mixed infrastructure networks, or in cases where vendor neutrality is part of the organization's procurement strategy. From a performance and redundancy standpoint, LACP provides measurable benefits. If a link in the bundle fails, traffic is automatically redistributed across the remaining active links without user disruption. This is particularly important in server-to-switch or switch-to-switch connections that must maintain high availability. Load balancing across the bundle improves throughput and optimizes resource usage. The ability to handle failure gracefully and continue operating under partial link capacity makes LACP a critical feature in enterprise-grade deployments where reliability and uptime are non-negotiable. In summary, port aggregation using LACP is a standardized method of combining multiple physical connections into one logical channel for improved bandwidth, redundancy, and manageability. It simplifies network architecture, reduces the risk of loops, and ensures consistent traffic flow between devices. Whether in the core, distribution, or access layer, link aggregation provides a scalable and fault-tolerant design pattern that aligns with enterprise network demands. The combination of automatic negotiation, dynamic recovery, and load balancing makes LACP indispensable for high-performance networking. To conclude, LACP is the protocol that makes dynamic port aggregation possible. It ensures that physical links are compatible, manages the formation of port channels, and maintains operational integrity across diverse switch platforms. Proper configuration, verification, and ongoing monitoring are essential to leveraging the full benefits of link aggregation. By understanding how LACP functions, how it integrates with VLNs and spanning tree, and how to troubleshoot common issues, you are better equipped to design and maintain robust network infrastructure for modern enterprise environments. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.